Welcome to the second day of Shaping the City, Forum for Sustainable Cities and Communities. This is the second and last day of the forum, and we are happy to host you, our audience in Palazzo Michiel and online through our YouTube channel. We would like to remind our guests in Palazzo Michiel to put their mask on, and if they like to have some water or coffee during the conference, please, next door you can find everything you need. And if you have questions, please ask our staff in Palazzo Michiel. Today, the conference is going to be split into two sessions, which are building through technology in the morning and architecture for the people in the afternoon. To launch this second day, we would like to present a project which is currently exhibited in a Time Space Existence exhibition in Palazzo Mora, and for which we have produced a special video. But before watching this video, we would like to have in our screen here behind us Steven Lamp, who is a designer and environmental activist from South Africa, founder of Noncrete, who will talk a little bit about what we're going to watch later.
Warm greetings to you all from Cape Town, South Africa. My name is Steven Lamb, co-founder of Noncrete, a company based in South Africa, specializing in alternative building materials and methods. Today's cities are ever growing, especially in the global south, inducing massive construction activity. Next to water, concrete is the most consumed material on Earth. To satisfy these needs, we need feasible and environmentally sustainable construction materials, the use of local solutions, and if possible, to enable synergies between sectors for maximum environmental benefit. In South Africa, and certainly beyond, invasive alien plants are threatening the indigenous ecosystem while exacerbating water security by affecting water surface runoff and fueling wildfires that release carbon into the atmosphere. Bio-based construction materials can turn buildings into carbon pools. This we know. However, the dynamics of using bio-based materials at the urban scale are not yet well known. The video you are about to watch will focus on a new type of structural and non-structural bioconcrete, or Noncrete as we refer to it. Using the chipped biomass of alien invasive plants and purpose-made special blend binders as substitutes for conventional sand, gravel and cement. The optimized mix design using invading alien plants as an alternative resource, combined with a policy that promotes multi-story buildings, offers great potential to achieve near-carbon neutral cities, clearing land of invading alien plants, and thus saving annual water surface runoff. Wood chips of invading alien plants are but one of many sources of alternative construction aggregate. When we look at waste material as potential building material, we see a world full of opportunity problems. Through this lens, we can look to re-engineer our built environment through a diligent process of rematerializing it. A material innovation alone, no matter how advanced, will not achieve the impacts we are wanting and needing to make. By way of example, I live in a country with the Gini coefficient of 63, the world's highest, making it the most unequal country on earth. This year, our unemployment rate was ranked the highest in the world at 44%. When we talk about shaping a city, we also need to ask whose city, and how are we addressing and including the basic needs of those living in this city. Clearly, inclusive, beneficiary-led planning and design processes become important. So too does a focus on safe, dignified and affordable housing. The upgrading of inner city slums, without the coerced removal of the urban poor, also becomes important. Design has so much to do with intention, and intentions can connect us, much like bridges do, and intentions can divide us, much like walls do. Clearly, we need to build upon common intentions. In a world capable of achieving the spectacular designs we see all around us, shaping a sustainable city, and indeed a sustainable world, is first and foremost a world where everyone is good enough for good design. In doing these things, we also need to better understand how to optimize the use of alternative building materials. Simply put, how to do more with less, without compromising on structural integrity, aesthetics, and quality. Here, our collaboration with the Block Research Group has proved essential, and it's thanks to their ongoing support that we have a much clearer understanding of how to create more with less as we go to scale. There are several hundred apartheid-era staff accommodation units in the Kruger National Park that are in desperate need of upgrading. We are proposing a pilot project in the park, the aim of which is to demonstrate the acceptability of using alternative materials and building methods in the construction of housing. The intention is to replace the existing structures with more dignified and sustainable housing, manufactured from locally harvested invasive alien biomass, thereby contributing to the maintenance of healthy ecosystems. I hope that you will find the video that follows of interest and value. If you'd like to join us or actively support us, please do so. We need your support, both big and small. Thank you for listening, and thank you to the ECC for the opportunity to share our work with you.
The contents of this project are definitely related to what we're gonna hear today in the two sessions. The video you're going to watch now is produced by the European Cultural Center and realized together with Plain Sight. So enjoy. And it's the first time that we present it.
If design really is good enough for everyone, then it needs to prove that it is good enough for everybody. And this is, I think, a real responsibility for designers, for architects, engineers to take this into consideration. You know, when you work with alternative aggregates to concrete and you start exploring the parameters and what's possible with the woody biomass of alien invasive species, and in the clearing of these plants, the restoration of natural ecosystems, the creation of low-tech, unskilled jobs, how we include people in that, all of these things actually come into a material mix design. We were very lucky to be noticed and by a national government and to be recruited into the Department of Environmental Affairs. Cape Town, like many other cities in South Africa and around the world in formal settlements, suffer the effects of ongoing devastating shack fires. Where shack fires can spread incredibly quickly. Wood chip is half the weight of commercial concrete. The thermal properties are double that of traditional concrete. The noncrete that we're referring to here is 3 times more fire resistant than commercial alternatives.
Stephen, I recall that I directly understood that the material that you were describing really had an opportunity to change things, that had a significantly lower impact. Really liked the idea of actually turning this bio-waste into something productive. I immediately saw that our notions of reintroducing the arch, so strength through geometry, that these principles are particularly relevant in a context like yours, where you want to do as much as possible with as little resources and cost as possible.
Geometry-based design is quite powerful for me in that it introduces the opportunity of woven formwork as an alternative to steel.
We can reduce very significantly the amount of steel reinforcement, but also the amount of cement. And so both of those are not only the expensive parts, but also the polluting parts. What we see in the exhibition is actually just some prototypes towards a real project.
Here we have several cube samples that were made with the invasive alien plants as an aggregate. You can clearly see the plants inside when the piece was cut.
We developed this brick, and it's only a first generation that allows anyone to build these safe structures stably without any formwork.
The click brick itself, the shapes that elegant, robust geometry-based design present are refreshing breaks to the typology that we've experienced so far. In developing countries,
using your hands is not a demeaning activity. It's actually a wonderful thing to do, and it's highly necessary and appropriate in the global south.
What you're seeing is nothing else than a reintroduction of the very robust geometries of a vaulted roof, and then we add these buttress walls that can help take some of the horizontal thrust of these floor systems. This is also part of the system that we developed together with Steven, because it was important to be incremental.
This is one of the first prototypes for how to make the formwork system for the woven shuttering. As soon as you see this hanging system in the air, it just shows how light it is, how delicate but really strong and effective this method could be.
There is an opportunity to activate local arts, local crafts, these basket weavers. What can we do to make this material also be celebrated? Because we are developing a repeatable construction system.
What we always consider like formwork as like a secondary system to realize the building. In this case, this product can immediately become part of the structure itself, and the formwork becomes part of the building. I think that's a very powerful message on so many levels. Locally sourced, locally made, completely recyclable, reusable as well.
and when I saw all these wonderful curves and freeform roofs and arches and these breaks in monotonous typologies that we get so entrenched in, I got very excited with what we could potentially do.
Actually, we are presenting structural systems, but we present them with materiality. The exhibition focuses on the materials, on the prototypes, but I hope that people will also take the time to look at our concept drawings and the plans of the project in the making, because actually it's not just about the vaulted floor, it's not just about the click brick, but also if you look carefully, you will see that we have this very disciplined way of using these shear walls, these buttresses.
We want to change low-cost housing to, again, safe and dignified housing. And the demonstrator model in Kruger National Park is trying to change the landscape of how we define and how we understand social housing and the opportunities that can come with a different approach.
I really believe that we're up to something here with this collaboration, and that is why I thought we have to absolutely try to be part of this architecture exhibition, because people need to be aware of it. This can be adopted by everyone as a safe system, a system that they trust, a system that they find beautiful, something that really can be a solution. I see this just as a first step. This is just us showing our way towards a bigger realization.
So thank you to Stephen Lamb and to Professor Philip Block and Junie Lee for being part of this video. And now we invite you to visit the exhibition later on in Palazzo Mora, and we move to the first session of the forum today. So Hadi, can you tell us more about it?
Thank you, Lucia. Indeed, very interesting video showcasing these new materials and, the geometry-based design as an opportunity for new construction materials. So with that, we will start our first session of today, which is Building Through Technology. To have a bit of an overview about this theme and this panel today, as you all know, that the built environment and the construction materials have proven to be one of the most significant contributors to global warming and CO2 emissions. So having a healthy planet and building sustainably, achieving equity and environmental justice are the pillars that the architects and designers are working to achieve. So with this theme, we explore the possibilities of new sustainable and vernacular materials as a construction solution. It demonstrates the latest trends and improvements in architecture technology, innovative materials, and parametric design. So with this panel, we will experiment materials such as bamboo, paper, other 3D printing and parametric design, and more 3D printing and 3D printing materials to be used. And online, we will be joined with Thomas, who's going to explain to us about an executed, very large-scale project, which is the Future of Us Pavilion in Singapore. Unfortunately, Wael Al-Awar, who is the curator of the UAE Pavilion for the 17th Venice Architecture Biennial and the recipient of the Golden Lion, couldn't be able to join us today due to family reasons. He sends his regards and he apologizes for that. But he were to share with us about using alternatives for cement as a construction material. With that being said, our moderator, Mariana Popescu, will share with us and will moderate this panel. Mariana, to give you a brief introduction about her. So Mariana is a tenure-track assistant professor of parametric, structural design, and digital fabrication at TU Delft, with a very strong interest in innovative ways of approaching the fabrication process and use of materials. Mariana, the floor is yours for this session. Thank you very much, and we're very much looking forward to see the discussions today. Thank you.
Thank you, Hadi, for the wonderful introduction. Thank you, the European Cultural Center, for the invitation. I'm really glad to be able to open this Building Through Technology session today, and I'm looking forward to the conversations with our panel's member here, which I think will be very interesting and will help us really explore and discuss the relationship between design, materials, and the technologies that bring innovative concepts to life. So much like the panel here, I come from from a context that is multidisciplinary, and I wanted to give you a little bit of a thank you. A little bit of a background of where I started from before going to TU Delft. So I was also at ETH at the Block Research Group, where there's a marriage between architectures and structure, and also within the NCCR digital fabrication, where there's a will to push the construction sector forward through digital technologies and new building processes. So really, the work that I do, or my background, lies at the intersection of architecture, structure, computation, and fabrication. Always striving to couple good geometric form with being materially efficient and using material effectively. So our discussion today falls on the all too common or very well and familiar known backdrop of the construction industry's impact on the environment. The fact that the sector is one of the largest contributors to climate change, being responsible for a large chunk of the energy and process-related CO2 emissions, and being faced with two contradicting challenges. So that on the one hand, and the projected need for having about an increase in infrastructure. It is projected that 3/4 of the infrastructure that would be there in 2050 is yet to be built. So at the same time, that means that we have a challenge of needing to really reduce, having an imperative need to reduce and be more efficient with the resources that we use, while at the same time somehow becoming more productive. So these things really go go head to head. Now, productivity on its own in the construction industry is a challenge, and that happens to be because the construction sector is one of the least productive ones. This is said to be mostly due to a lagging behind in digitalization. So really, the construction sector is faced with two challenges, the environment and digitalization, meaning that digitalization is key in all of the aspects of the construction sector's value chain, and it's something that we need to address. Now, usually when we talk about digitalization, we very often think about design. The truth is that when it comes to design, we have an abundance of computational tools to help us design, both architects and engineers. So much so that we are indeed able to create really complex structures and also build those. However, no matter how interesting or exciting those structures may be, the current paradigm that anything is possible, that design is about a subjective form, and that engineering is there to prove and make sure that that form stands at all costs, has to change. We simply cannot do things this way. And it is indeed beginning to change towards designing where we still keep elegance in mind, so we're not taking design out of the question, but where we are also mindful of being efficient and economical, and I'm speaking here mostly in terms of material then. That means that we need to look at new materials, be as efficient as possible, and use those materials as well as we can, and only where we need them to be. That means that we need different specialists from different areas to come together, to join forces, and to be able to come up with new, innovative, and sustainable solutions, not only for design, but also for fabrication and construction in general. So with that in mind, what I wanted to show you today as part of my work actually deals with the challenges associated with building complex concrete structures. If we think that we can design something that is materially efficient, usually those geometries are also complex. They're not the usual simple right angle flat geometries that we know. So when it comes to building those, we need to avoid the problem of shifting our material inefficiency from the structure itself to the way it's being built. Because if we do look at how these structures are built in reality, we find a system that has remained largely unchanged for the better part of a century. They require molds that, even though we are a lot more efficient at producing and a lot more precise and a lot faster at doing, the bottom line is they're still big, clunky molds that need to be held up by a lot of scaffolding. They're labor intensive. And if we consider that we build these geometries only once, they turn into a pile of waste. So it is actually no surprise that a lot of research, both in academia and in industry, is really geared towards how can we construct these types of geometry better. So how do we look at formwork? There are several examples, whether it is on looking at how we produce faster, lighter, how we can have reconfigurable molds, 3D printing, which can do almost anything, or really looking at solutions where where the formwork is left in place and becomes an active part of the structure. This is more or less a development along the traditional lines of formwork or molding for concrete. Another option or another avenue that has also been investigated for a while, but in lesser means, is using a membrane, flexible formwork systems, where that membrane is tensioned to give the shape to the geometry that we want. That can be done either by draping a membrane or a textile in this case over frames, by inflating that into shape, holding it up with splines or cables, or simply having rigid frames that hold it into shape and then use it to cast concrete. In going away from a rigid formwork system to a flexible one, we gain certain advantages. First, using a membrane is a lot lighter than wood. It's a lot less wasteful. We need lesser foundations and a lot less props. There are some caveats to that. If on the traditional side, if you can produce the mold, you can also produce the structure. With a flexible formwork system, that's not always the case. So you cannot produce just any geometry that you want. It also has to be one that works with a flexible system. Now, I like to think that that's a blessing in disguise, because if we want to take advantage of a more efficient construction system, we also need to think of having a better design of our structures, and usually that means that they're more efficient in terms of the material they use. So, just to be very brief, on the membrane side, usually what's being used is a woven fabric. It's usually a flat sheet, it's a single layer, and it has very directional properties, because woven textiles have these 90 degrees grids that can shear and be put together. How this is done is you take flat sheets of material, you tailor them much like we do clothes, and we get them into the geometry that you want. You can imagine that this can also be challenging in terms of how do you get this out of flat packed pieces. On the other hand, if we were to use a knitted textile as part of these types of formwork systems, we have a few other opportunities, meaning it's a different textile formation system which allows you to make 3D geometries in one single piece without the need to stitch too many pieces together. You can have branching structures, pockets, spacers, and very importantly, or very interestingly, tailored material placement. And when I say that, I would like you to all think of the bottom right side, and of all of these kind of historically lacy materials, because that is exactly what this is. You can put the material where you want to put it, and that's where the strength of this kind of technique lies with minimal waste. So how this works is we start with a design, hopefully structurally informed one, so that we are efficient. For that design, a knitted textile is a fitted textile is made using existing knitting technology, so existing machinery. That textile is then tensioned into shape, as I mentioned before, and it is coated with a thin cement paste coating or another coating that gives it an initial rigidity. And that's because a knitted textile is a lot softer than other textiles or things that we know, and definitely a lot softer than wood. So we need that rigidity to be able to cast concrete afterwards. That rigidified mold textile then becomes the formwork for concrete. There are two challenges. One, getting from the design to the knit. That still means that we might need to discretize our shape into different pieces, because our geometries or our buildings are a lot bigger than the machine itself. But within those pieces, we still have 3D geometry. And then figuring out a way to give those instructions to the machine to produce the textile, the fitting textile that we want. The second part, once we do have this, is how do we get from that textile to the formwork? And there are simply maybe two avenues for this. On the one hand, textiles are compact and easy to transport, so we could just put them in a box, in a backpack, in our suitcases, send it to the working site, tension that, coat it, and have the formwork. Another option is to do the same, but then for the different components in a very controlled, prefabricated environment, and then have those very lightweight, compact components transported to the site, assemble them, and create the formwork. Whichever way you choose, that would be then used to cast the concrete structure into it. So what I wanted to do is show you that we've tried this on a breadth of examples at different scales, and I wanted to pick one of them, the one that's in the middle. It's Knit Candela. It's a shell structure that's been built in 2018 in Mexico City. It's an homage to the famous shell builder Felix Candela, which was using hypars that you could do out of straight sheets of material. In this case, it's not a hypar, so it shows that we can do non-developable geometries with this type of forming technique. So what is special about it is that it was built on a cable net and fabric formwork, and those two weighed together about 55 kilos and carried the 5 tons of concrete. What is particularly interesting about it is that it is a waffle shell, meaning that it has a thin 3 centimeter concrete shell with rib stiffeners in 2 directions. And what the challenge here is, or what the forming system here shows, is that we don't only deal with the globally doubly curved geometry, but we also start dealing with the local intricacies of a geometry to be able to create these cavities or rib stiffeners. So very quickly how that was done was by creating a frame, a wooden and steel frame, tensioning a cable net and fabric into that frame. The fabric, the textile had already channels to have integrated the cables and pockets for inflatables, which would create the cavities. It was then coated on one side with a fast-setting cement paste, and once that hardened, concrete could be applied in relatively traditional ways to it. Once the concrete hardens, you can remove the frame, and you're left with the structure. The frame could be reused or recycled, and the fabric stays in. What you see that the pockets, the inflatable pockets, did become the cavities in the concrete, and the textile stays there. It's also the little blue line that you see there, and it's also what you see on the inside of the pavilion. So really, the fabric in this case had two functions. On the one hand, it had a technical function, and on the other hand, it had an aesthetic one. The aesthetic one is simple, you can see it. The technical function on the other side controlled the degree of inflation, controlled the openings of where to pass the cables through exactly, the nodes where they should meet, and all of these types of features. And this is all done in one single fabrication process. We took advantage of the fact that you can create this type of geometry in one piece, but you are limited only by the width of the machine and can otherwise create an infinite piece, and divided the geometry into only 4 pieces, meaning there are only 4 seams over the entire geometry, and produced that on an industrial knitting machine that looks something like this. What you can see is that we produced arguably the world's largest scarf in 4 pieces, and packed that appropriately into 4 vacuum bags that could be brought easily to the construction site. This is also because we're architects, so we finished the night before, but it helped to show that we can really pack this in our checked-in bags. So once there, all of the cables, all of the different pieces were put together by a local seamstress, which was very happy not to work on the usual tailoring for one day. And then we passed all of the cables through the 4 pieces of the textile, also fixing the nodes temporarily. Here you can see them coming out. So that we would know how to get that geometry. Once that was done, we took it outside and hoisted it into the frame. Now, it looks like a heavy thing, and a lot of people, it was just us being very careful. It's 55 kilos, but we were doing it for the first time, and we wanted to make sure that it's right. And there you can see the tensioning of the system. What I really like is this photo, and it's something that still does something to me. And it's because it's the moment that I could see that textile stretch to the actual size that we wanted it to, but also you can see a lightness. You can see the lightness of the formwork of 50 square meters and how you can get that into a complex geometry. I would find it very difficult to imagine what this might look like out of EPS milled foam or timber, and how much scaffolding that would have needed. Then it was coated, as I mentioned, on one side with a very thin special cement-based coating. Who you can see here is Lex Reiter. He's the concrete magician that also developed that coating. He's with the physical chemistry of building materials at ETH and makes that possible. So once that's hardened, what you see is actually a beautiful Swiss chocolate, which probably nowadays will turn into Belgian chocolate because I live in the Netherlands. And what I wanted to point out here is that those pockets you see, or those bumps that you see, are the cavities that come out then in the structure later. What is also interesting to explain is that usually when we talk about digital fabrication, or where we talk about mass customization, we say that machines don't care if they produce 300 times the same geometry or 300 times a different one. And that is completely true, but what is not easy is then the logistics on site. We need to label those, and we need to make sure that those go into the right place. In this case, that intelligence and that logistical part was taken over by the textile that had this control built into it, so we don't have to do it ourselves. Here you can see the concrete being applied. I guess I'm running out of time, so I'll go a little bit faster. And then you can see the beautiful structure emerging out of it. What I like is to see the contrast between the textile and the concrete, and I would say that the workers did a fantastic job, and Candela would have been jealous of the surface of the concrete himself, I think. Some of the takeaways from the project are that the formwork itself, so only the textile and the cable net, excluding the timber frame that could be reused, cost only around 2,250 euros for 50 square meters. It weighed 25 kilos and was easy to pack to get there. It took 36 hours to make of machining time to make the textile versus what takes about 750 hours in terms of milling or producing a similar surface area. And the whole project from beginning to the structure standing there took about 3.5 months. So in terms of productivity, this would have really been impossible with traditional techniques because 750 hours is roughly 3 months if you work only 8 hours a day, which we never do. I don't know why that came here, but these are the hidden slides. Well, in any case, there are two challenges in this. So if we had a look now between the challenge of how do we get from a knit to the construction, the second challenge is how do we get from the design itself to that knit. Because we use machinery, so we really need to get these pipelines of how to fabricate. So in that case, the machine takes a thread, has a needle bed, goes back and forth over those needles to create the textile. And because of this, it can place material exactly where it's needed. What it usually takes as instructions are a set of bitmap patterns that look something like this. So every line is a pass of the machine, and every little pixel is one needle adding material. And where you don't see a pixel working, where you don't see any pixels, so where you have all of these kind of white lines, is where material is not being added. And that's what really allows you to create these 3D geometries without needing to cut and sew pieces together, because that cutting and sewing is being done automatically on the machine. Now, these patterns are usually done by hand, knowing exactly where to place these features, and it may be very easy to do this for primitives or geometries that we know, or small scale things, but when it comes to the architectural scale, that becomes tricky. So really, it is because we're not necessarily based on primitives, and it is a bigger geometry, so you want to do this in a fast way. So really coming up with a computational pipeline that enables you to know that the geometry that you've designed is also the one that's being instructed to the machine to create is one important aspect of being able to build this way. Now, if we have a computational pipeline, which is part of the development I did for this project, and will be also shared open source, it means that we don't even need to carry that 25 kilo formwork with us, but we can simply send the instructions to the machines locally because they do exist all over the world and not just one somewhere in a university. So with that example, what we were trying to show is that you can build in a light way that is fast to produce. It reduces waste in terms of the construction waste, so in the building process, and we can build with minimal intrusion because it's light and easy to carry in. Now, there are a few other points that using a textile can help is functional integration, and one of the simplest things to look at is reinforcement. So the next step would be to look at how that stay-in-place formwork is not just a lost one, but one that is actually also taking out the steel and acting as reinforcement in the structure. This is done in collaboration with Minu Lee from ETH and looking at how that can become reinforcement. One of them is to look at how we can introduce these kind of straight lay-ins that become active in the structure, and how we can create features that make a better bond with the concrete so you don't take it out as easily. Other than that, what we're also looking into is how to translate these types of things from the big crazy geometries to more recognizable elements for day-to-day. So we're looking into how you could do this for a normal rectangular beam or an I-beam, how you can use these types of features to guide maybe traditional reinforcement or make sure that the stirrups are in exactly the right place for geometries. These are just some examples of that rectangular beam and having the reinforcement coiling outside and done in a single process, or the I-beams where the stirrups, where the shear reinforcements are already laid into the textiles precisely at exactly the right spacing, with exactly the right size, and where we can guide easily normal reinforcement through. That is also then coated and cast, and here you can see the less good-looking architecturally, but very interesting structural experiments for I-beams using this, so that it's really an exploration of how we can make this more efficient in a way that we also recognize in construction today. Now, to close, this is a project that is being developed, but exactly for that purpose, to really look on how this could be applied in a more real context. And that is also important because it's being done together with industry. It's being done with Basics and Rijkswaterstaat in the Netherlands to be a real pedestrian bridge that is being implemented there. The design for it is inspired by Robert Meyer's Herkinatobel Bridge. The structural principle, but in this case, it's a 3D shell action that looks something like this. In this particular case, what we're also trying to do is explore what kind of alternative materials can be used so that it's a really fully circular design. If the knit can be removed or the formwork can be removed, and what that means in terms of the end of cycle for this particular structure. I went a little bit fast through it. In terms of construction, it would be made with a knit that is deployed with bending active systems. It wouldn't need any support from the bottom. It looks, this is from an earlier experiment, so it's just to kind of let you imagine what that might look like as a deployable system, where you can create these structures in a way that doesn't hinder the flow of either water or transportation in general. So in doing so, we're looking at, again, at those types of sections that are more recognizable. This is just a test for a triangular section in that case. But also as a teaser, I wanted to show you that we're looking at the materiality of it and how that goes into the context of rib-stiffened shells, for example, or things that we might recognize in our day-to-day life. And there's an upcoming project in Rome coming on this topic. So with that, I would like to thank you very much, and also go to our speakers for today. So first up, we have Marirena, which I also very well known from ETH. Marirena is an architect with a strong interest in novel approaches to design based on digital fabrication. She's a PhD researcher at the Chair of Digital Building Technologies at ETH Zurich, where she researches additive joints for spatial lightweight structures. She holds a diploma from the Architectural Engineering from NTU in Athens, and a master's in advanced studies in architecture from the digital fabrication section at ETH. And before joining ETH, she was a visiting research at the Transformable Intelligence Environments Lab at TUC.
Thank you very much, Mariana. Can I have maybe the pointer? Thank you very much for the introduction, and I would also like to extend a big thank you to the ECC team for the invitation. So today my talk will be about systems and systematic thinking in architectural practice. So by the year 2050, according to the United Nations, the world population will reach an estimated 9.7 billion. And by the year 2030, the UN Habitat estimates that 3 billion people will need access to adequate housing. That is 96,000 new housing units every day. And the majority of those people will live in cities rather than rural areas. Some of the largest cities that we know today will transform into megacities, and some have not even been built yet. One of the biggest problems that we are facing today, planning for the cities and the buildings of tomorrow, is the access to materials. We are seeing natural resources like sand, which is used in concrete mixes, being drained as we face a reality of material scarcity. And concrete alone, the material that dominates the construction industry, is expected to contribute to 12% of the global greenhouse gas emissions by 2060. China alone, in 3 years, used more concrete than the United States did in 100 years. And you see, global material use is expected to more than double by 2060. Something between 40 to 50% of the resources extracted for global materials are used for housing, construction, and infrastructure. Materials like concrete, that once projected a modern ideal of the future of efficiency, urbanization, and sustainability, have now become a key component of the problem. And if I wasn't clear thus far about our share of responsibility in all of this, let's look at some facts. The construction industry today is responsible for 40% of the global carbon emissions. Looking at the energy consumption of buildings, currently 80% is embodied, while only 20% is operational. This balance is expected to reduce to about 50-50 in the next 30 years. So how do we achieve that? The step into the future cannot be one single solution. There is no holy grail or secret recipe that can fit all. This is the reason I promised today to talk about systems. We architects need to change the way we think, plan, and design. We have been raised to talk about function and form, but what we should be talking about is interactions and dependencies. We can take example from people like Howard Odum that discussed energy and revealed the workings of information, biological, and social structures. Buckminster Fuller, who filed several patents describing new types of systems. And in the years to come, we witnessed more systematic thinking about buildings. Architects designed not only the envelope, but operational flows in the works of Fritz Haller, Renzo Piano, Regis Rogers, and others. But still, parts of the chain were missing. Parts that today we have the opportunity to trace, analyze, and develop thanks to digital tools and methods. With technologies like additive manufacturing, we acquire means to develop and design new systems for the AC sector. So I investigate the opportunities of additive manufacturing and how this technology allows us to develop new systems for space frame structures. So space frames are inherently efficient construction systems. They are modular and materials are used optimally for maximum performance. However, 3D printing allows us to tackle the rigidity of existing proprietary systems, embedding many more parameters into the system. So when we start a design, we rarely think of all the factors at play. Our decisions are not local, but affect our environment before and after the life of the buildings we design. We like to think of architecture as a local endeavor, but that is only one facet of it. So zooming in on the topic of space frames, we can identify at least 4 different parameters that allow us to better understand the system and its economic, ecological, and social footprint. Design, materials, manufacturing, and assembly. Those can be diluted into interconnected impact factors. 3D printing allows us to encapsulate the formal and functional complexity of a structure in its connections. We can assume that 3D printing technologies will only grow from here. They will become more accessible, while the price of products will decrease. And based on that assumption, we can envision a sustainable model where digital design allows us the following prefabrication scheme. We can 3D print all the connections in the nearest available 3D printing facility. We can ship those parts to the construction site with minimal carbon footprint, as they amass only a fraction of the volume and the weight of the total structure. And near the site, we can prefabricate modules using set connections and local materials that are later mounted in a quick and efficient fashion on site. So as we're in Venice, I think it's appropriate to discuss our exhibition piece here, the digital bamboo, and how it reflects this vision. So the pavilion is a bespoke structure that is made of unprocessed bamboo canes and 3D printed connections. It covers an area of 40 square meters, but it only weighs 200 kilos. So why bamboo? I mentioned local materials, and local materials can be standardized elements that are produced close to a site, but they can also be biomaterials available in the land. Biomaterials offer an alternative construction product which is typically biodegradable at the end of life, helping to regenerate natural systems. And such is the case from bamboo, species of which can grow up to 60 centimeters within a single day. Its growing and harvesting cycle is only 5 to 10 years. It is therefore a scalable material for a sustainable way forward. Sociocultural perceptions often associate local biomaterials with undesirable or old-fashioned aesthetics rather than modern lifestyles, which are often linked to concrete, steel, and glass. Furthermore, bamboo is believed to be only a South Asian product. But what if I told you that this forest is in France? Farming of bamboo is becoming more popular in Europe and North America as efforts are being made by countries to include it in the building code. And we have seen bamboo trusses being made in unconventional ways by filling cement in the poles to connect standardized systems or meticulously fabricating exoskeletons. But bamboo is such a lightweight material that perhaps industrial metals and intricate exoskeletons are not needed for joining canes. Looking into the available 3D printing methods and materials, we identified a method called multi-diffusion as a possible alternative. This is a powder-based system of very high resolution and accuracy that manufactures high-strength nylon part, as you see in the picture. They're extremely lightweight and sample compression strength more than double than of regular concrete, actually. And we started designing with these materials, working with students of our Master in Digital Fabrication at the ETH to develop a new connection element for bamboo. So the first informal structural tests that we made were actually quite disheartening. Exactly, we tested trusses and cantilevers that held an approximate payload of 20 to 100 kilos. At this point, we joined forces with the chair of structural design to improve the system by iterating, testing, and improving the geometry of the connection system. Our starting point was this idea, which we found the most promising. Bamboo canes could be used unprocessed and connected to the joint with a few cuts. The elements fastened together with inexpensive means like zip ties. A series of intensive testing drove the evolution of the jointing system to a more and more detailed solution into a more modular approach. And after about a month, we were able to go from the state on the left to what you see on the right. So a fully reversible, rotation-free modular system that can click together like Lego pieces is fastened by inexpensive and removable means. The joint consists of standardized parts that can be mass-produced and a minimal custom part which contains all the relevant informations and logistics for assembly, while it integrates all the other layers of the structure like post-tensioning members and shading panels. So more than 2,000 elements were fabricated within a month, and our kit of parts was ready to ship. All packed in 4 boxes, we loaded everything on a truck and came to Venice. 6 modules were pre-assembled and mounted on site within 1 day. Thanks to the intuitive system, people also from the ECC, as well as other workers with zero expertise or knowledge of the system, helped us to assemble this unique structure. So in retrospect, let's see if and what we managed to achieve with this research in regards to the questions that I raised in the beginning. We used monomaterial elements to avoid layering and composites. This ensures that there is no cross-contamination between the different materials during disassembly. Therefore, materials can be recycled or reused. We avoided the use of higher than needed quality materials, minimizing the resources. We used a local biomaterial from a Swiss provider instead of carbon-intensive steel or aluminum. We also developed a modular structure that can be assembled on site from components that are manufactured off-site, thus supporting safe and rapid deconstruction and material use. We sheltered the space with minimal volume, weight, resources, and we made it happen with a low-cost but high-tech system with a small carbon footprint. Now, you might ask, is this the future of construction? My answer is probably no, but perhaps this is a part of it. And learning to design in systems instead of buildings and using the opportunities that new technologies offer, we can design today for not only for tomorrow, but for the next 50 years. So, thank you.
Thank you, Mariana, for the wonderful presentation and the reflection of what it can mean for construction. We're going to go next to Thomas Schupfer. He's joining us online. Professor Thomas Schupfer obtained his doctoral degree and master's degree with distinction from Harvard University. He began his academic career at Harvard's Graduate School of Design, where he was appointed Assistant Professor of Architecture in 2004 and Associate Professor of Architecture in 2008. He was named full professor after joining the Singapore University of Technology and Design in 2011, where he is the director of the university's award-winning Advanced Architecture Laboratory. He is the recipient of prestigious awards and recognitions, including the President's Design Award, Singapore's highest honor accorded to designers and design across all disciplines. So with this, I give you the word.
Thank you very much, and good morning from Singapore, or good afternoon from Singapore. We're about 6 hours ahead of you. Thank you, the European Cultural Center, for having me, and thanks for the nice introduction just now. As we heard from the previous speakers, for quite some time now, computational design has significantly impacted architecture in multifaceted ways, most noticeably through the rise of algorithmic and parametric methods. In conjunction with these advances, new fabrication tools and techniques have made customization of building components easier, allowing for new formal languages to be explored in architecture. In this context, the design and construction of the Future of Us Pavilion, shown in this slide, presented a great opportunity for our Advanced Architecture Lab at the Singapore University of Technology and Design to explore the potential of these advances. Located in Singapore's Gardens by the Bay, the Future of Us follows the tradition of architectural structures that evoke a dialogue with nature by blending an intricate form with a perforated skin fluidly with the adjacent environments. For visitors, it offers a climatically comfortable outdoor environment and a stunning visual experience akin to walking under the foliage of lush tropical trees. Originally built to house the Future of Us, Singapore's 50th anniversary capstone event in 2015, the pavilion has since become a permanent landmark that continues to serve as a public asset and venue for important community and cultural events. There's a clear mathematical logic to the design of the project that we determined by extensive environmental simulations and structural optimizations. So in the following short presentation, I will share with you some more visuals of the pavilion. I will then briefly discuss important steps in the design, development, and implementation of the project, and that will be followed by a discussion of the pavilion's reception and current use. Let me start with the visuals. Here you see the pavilion in an aerial view from above. This is an aerial view of the project from the west. This and the next two slides show you the interior of the pavilion and hopefully convey a little bit what the experience is like to be in this structure. And here you see the pavilion at night in a view from the south. For those of you who do not know Singapore, in the background you see Marina Bay Sands, a very large project by Moshe Safdie. And this is the last of the visuals I'm going to show with you initially. This is another shot that was taken at dawn of some of the interior of the pavilion. The research that led to the design of the pavilion already began in 2013. Here you see some excerpts from our winning competition entry for temporary structure for Archifest, an annual design festival organized by the Singapore Institute of Architects. The project was designed for Dhoby Ghaut Green, a popular public park near Singapore's famous Orchard Road. Based on the environmental and structural analysis, we proposed an open structure that is dense in certain areas where it is exposed to the sun or rain, for example, and open in areas where prevailing wind can enter or where particular views from the inside were of interest. The idea of an environmental fine-tuning, if you will, of the architecture is achieved through triangular units that vary based on the need to allow for natural light, wind, views, etc. This is essentially how this plays out then, this kind of densification within the triangular units that became the base element for the structure. And here you see the proposed complete structure in a view from above in a drawing. And this was then translated into a 3D printed model that you see on this slide. An invitation to showcase this project at the Time Space Existence exhibition at Palazzo Bembo in the context of the 2014 Venice Architecture Biennale allowed us to further explore how the ideas we had developed for our Dhoby Ghaut Green project in Singapore could be realized at a larger scale. We constructed the geometrically complex form of the enclosure from laser-cut aluminum sheets that were folded and subsequently assembled along their edges. On this slide, you see an example of the cut sheets. On the previous slide, actually, you see the cut sheets that we produced. And on this slide, you already see the two of the resulting triangular modules in our workshop prior to them being shipped to Venice. This slide shows you the fully assembled prototype in Palazzo Bembo with the scale 3D printed model in the foreground. The invitation to exhibit at Palazzo Bembo in 2014 prompted a parallel invitation from the Design Singapore Council to display a prototype of our project at the National Design Center Singapore, where it caught the attention of the Future of Us curatorial team. Our lab was subsequently invited to design the Future of Us pavilion at the Gardens by the Bay, a project, of course, significantly larger than the prototype displayed at the National Design Center. So here on this slide, you see the prototype at the National Design Center in a night shot, and here the same prototype in a day shot. So you see, I think, nicely how the light is filtered depending on the lighting condition. As for the Future of Us pavilion, it consisted of an overarching roof and a linking canopy, and in the context of the Future of Us exhibition, conjoined a cluster of temporary exhibition domes that you see indicated here in ovals in the plan. By way of numbers, the pavilion incorporates 11,000 unique perforated aluminum panels, over 12,000 bolts, more than 11,000 plates, and more than 4,000 elements for the main steel structure. The project spans a width of almost 50 meters and reaches a height of 16 meters. In terms of thickness, it is a very slight 20 centimeters. Despite the project's geometric complexity and the resulting uniqueness of most of its parts, we were able to realize it in less than 6 months' time from design to completion. This was largely due to the extensive use of advanced computational methods that allowed for the parallel design of the project's steel structure and aluminum cladding, as well as the just-in-time prefabrication of most of its parts. The computational analysis of the pavilion's freeform shape led to its structural rationalization into vaulted arms and a central triangular shell. This enabled the structure to work as a fully triangulated series of arches and to behave like a hybrid grid shell. The vertical orientation of the arches in the arms and their radial orientation in the central shell subsequently allowed for the prefabrication of all members and their installation on site, using only a single easy-to-measure dimension as a control. We produced drawings for the steel structure, the cladding, the cut sheets, and the installation of the panels. The required close collaboration with other members of the construction team was achieved by using a shared lightweight and platform-independent computational master model, in that every structural element of the project was represented by a center line. This master model was also used to evaluate the triangulation of the overall structure in terms of its structural, environmental, and aesthetic performances. In terms of construction sequence, the project was assembled in 4 overlapping phases. In phase 1, one of the 3 arms was constructed. The central triangular shelf was constructed in phase 2, followed by phases 3 and 4, and that the remaining arms were built. All 4 phases were completed within only 3 months' time. For the installation of the aluminum panels, 2 crews were assigned to work between 2 grid lines at the same time, with one installing the external panels first, followed by the other installing the joining internal ones. This method proved to be efficient, effective, and highly accurate. So on this slide, you see the installation of the exterior panels, which only require cherry picker cranes. Here you see the pavilion's interior during the construction phase. In the center and on the right, you see the temporary exhibition domes that were part of the exhibition. And here you see the pavilion during the installation of the interior panels. The Future of Us exhibition was launched in December 2015. This photograph shows you the opening event with Singapore's Prime Minister Lee Hsien Loong. And here you see a detail of the finished pavilion's interior during the exhibition. Below, the white thing below is, of course, again, the temporary exhibition dome underneath. And this is an exterior view of the exhibition, again, with one of the domes in the foreground and the pavilion in the background on the right. Over the course of the 100 days long Future of Us exhibition, the pavilion had about 400,000 visitors. Many of them expressed that the pavilion should be kept after the end of the event. The Singapore government subsequently decided to make it a permanent structure. So what you see here on this slide is Gardens by the Bay, and on the left, the empty pavilion shell after the end of the exhibition. And here the same situation in a shot that is taken from ground level. Gardens by the Bay subsequently became the owner of the pavilion. So it was handed over from the Singapore government after the end of the exhibition to the Gardens. And the pavilion was then used for important events such as the annual Singapore Garden Festival. And what you see here is a shot that was taken during one of these events. In 2018, after already having received a series of national and international awards and recognitions, the pavilion won the President's Design Award, Singapore's highest honor accorded to designers and designs across all disciplines. This then led to a series of events organized by the Design Singapore Council that promoted the project both nationally and internationally. Here you see some of the advertisements for these events. The pavilion, as a winner of the President's Design Award in 2018, was then also featured in many public realms. And here you see an example that I like very much, which is from the Singapore subway train, or MIT as it's called here in the local context. So many publications of the project followed, including the one shown here in Better Cities, published by Singapore's Center for Livable Cities. A very notable publication of the pavilion in this context was in the special issue of National Geographic that you see on the left here, Singapore City of Tomorrow. And this special issue featured our project with the photograph that you see on the right as an example of cutting-edge architecture in Singapore. The pavilion actually kept receiving awards and prizes, and it also appeared frequently on social media platforms. And I think all of this in combination then led to Gardens by the Bay decide to make the pavilion the centerpiece of a new entrance to the gardens. And here you see a photograph that was taken during construction that led to the final design of the project that I shared with you at the beginning of my presentation. The pavilion is now one of the permanent features of the Gardens by the Bay in Singapore. You see it on the map on the left. next to the friendly cartoon face. And nowadays, the pavilion continues to serve as a public asset and venue for important community and cultural events. Here you see one example. It is used as a marketplace sometimes. And this shot was taken during the recent Dale Chihuly exhibition, where he suspended a beautiful glass piece from the ceiling. Interestingly, this event was co-sponsored by Porsche that displayed its first all-electric model in the foreground, quite a colorful version of it. And the final example of the current use of the pavilion that I would like to share with you is the spectacular Team Lab exhibition titled Flowers and People, Giant Lattice Mass from 2019. Team Lab, the Japanese arts collective, used the pavilion for an interactive large-scale projection. So let me just share this short video with you. So in summary, the design, fabrication, and construction efficiency, effectiveness, and accuracy achieved in the realization of the Future of Us Pavilion at the Gardens by the Bay, Singapore, testify to the great potential of building through technology in our field. This allows, of course, for whole new paradigms of exploration, not only to achieve innovative aesthetics and environmental responses, but also resource efficiency, precision, and structural tectonics that introduce new and exciting realms of architecture. Thank you very much.
When it's beautiful. We'll move on to our next speakers. That is David Andreen and Anna Goide. David Andreen is a senior lecturer at Lund University, where he leads the Biodigital Matter research group and is the director of the master's program in digital architecture and emergent futures. His research concerns architecture, digital fabrication, and computation, with a particular interest in how principles of biology can help shape new sustainable paradigms in the design of the built environment. David won his doctorate at the Bartlett, UCL, investigating termite mounds and models for complex functional form and related principles of emergence and self-organization. Anna Goide is a PhD candidate at Biodigital Matter at Lund University, where she investigates the potential of additive manufacturing in architecture through computational design. She received her Master's of Architecture from SITA studio at the Royal Danish Academy of Fine Arts, after which she has been teaching and working at studios with different strategies for digital fabrication. Her research met industry through design and co-fabricating one of the first 3D printed buildings in Europe. Her work explores the current relationship to the environment through the link between complex geometry and new material systems within digital computation and additive manufacturing technologies. I think the floor is yours.
Thank you very much. It's fantastic to be here and be part of this presentation, the group of work that's already been done. And thank you very much to the ECC for the opportunity to come and also for the opportunity to be part of the Time-Space Existence exhibition. So we will be talking about the potential of 3D printed architecture. And you've heard our introduction, so you don't necessarily need this. As mentioned, Anna was part of designing and building the first 3D printed building in Europe, which you can see a picture of here. And 3D printing of architecture is something that has moved very, very quickly from being something theoretical explored in academia by a few select academics around the world to suddenly entering the main stage of architecture and architectural discourse. And you can see a lot of projects being part of culture today, and you can see that a lot of companies are suddenly moving into it. But perhaps as it's illustrated by the example here, this very often it takes the form of concrete. Looking at this graph, you can see how in 1997, the first attempts at 3D printing architecture were made by Joseph Pegna, which then slowly was picked up by a number of other researchers. And as you can see, although this only goes to 2018, there's been an almost exponential growth in how much architecture is being 3D printed. We think, though, that at this time, when you can see this becoming mainstream, we need to think about the why. What is it that 3D printing, additive manufacturing can actually bring to the world of architecture? So not just making things faster, more efficient, and less costly, but building them the same way, but what new value can we actually add to the built environment? What different ways can we make through this technology, and how do we use it? As was mentioned by Mariana, my own background comes very much from looking at nature and particularly studying termite mounds. And I think this picture is a good illustration of what we're trying to do because it represents the kind of astonishing beauty of nature. Now, and then the unexpectedness of how it might look from the inside of a termite mound in this case. But perhaps it's not the form itself that interests us. It's not the way that nature looks, as you've seen very often being copied in architecture and indeed other engineering and design fields. But we need to look at the processes that lie behind these forms, how they're generated. And we need to understand how architecture makes things, because surprisingly, digital architecture allows us to come much closer to nature and how things are done there. We're going to be talking about two of our projects that are both presented here at the Time-Space Existence exhibition. And both of them have some of their origin within the termite mounds that I've studied in the past. The left one image you can see is a mound about 3 or 4 meters tall, so it's quite a big structure, created by macro termites in India. And this forms very much the foundation for the second project we're presenting. And to the right, you can see something that actually comes from the inside of a termite mound. This is what's called a fungus comb, and it's a structure that's built by the termites to harm their farms of fungus. Essentially, they're 3D printed by the termites from biomaterials, and the fungus lives on it. And you will see very soon how we've been inspired by this. So first, we're going to be talking about this. Yes, these are the two projects. But firstly, we're going to be talking about proto-mycokeon, which is then a project which explores the materiality and process of 3D printing, and particularly how we can rethink our material paradigm and how we use materials and how materials are becoming part of architecture. But this project has been very much created by Anna, so I'm going to leave the word over to you to explain a little bit more about what happened. So.
Yes, thank you. So through this project, we looked at sustainable production from the perspective of material sourcing. And so we realized the project through a printing process that we called BioFDM, Biofused Deposition Modeling, which is using fiber from plant fiber that is bound by mycelium. And it's important that this can come from a wide range of urban agricultural and forestry waste and byproducts that are then upcycled into architecture. And since it is biodegradable, it can be recycled, and it points at a circular construction. As well as it can be used as new fiber waste to be used through the same process into a new generation of architectural elements. So for this project, we collaborated not only with fungi, but with the biology department at our university, specifically the microbial ecology group. Yeah, so we collaborated with mycologist Dimitrios Flodas, with whom we've developed the protocol of biodesign and biofabrication. And here you can see the inoculation of the substrate. So the plant matter that is being inoculated with the living fungus. And then we 3D printed this. And it's important, we wanted to avoid using synthetic glues or plastics or chemically or thermally activated binding agents, and wanted to use the biology as a process of binding through growth. And here you can see at the end of the growth process, so after printing, it goes through a stage of growing, into which you can see the component is covered in mycelium, which is the root network of the fungus. And this transforms the material, so it becomes resistant to water, but it also absorbs moisture in the air. And so it is both chemically and mechanically transformed by the fungus into a new material. So in order to negotiate this, there's several needs of the fungus, which is oxygen, right? So it has higher needs of oxygen, and there's also requirements at the fabrication level for the printing process, and then, of course, architectural scale needs at human scale. And we negotiated these steps through complex geometry, and this has been through computational design that we use extensively, which allows us to link these separate scales and needs and to code relationships and processes. It's also important to note that the print process itself has its, of course, its tectonics, and its the end result comes from the process, right? So the print path and the layers that you see, but as well working with a living agent, with a living organism that is variable and dynamic and at times unpredictable, does result in the variation of colors and textures and that give the final materiality that is very much process driven. So our other project is Meristem Wall, and David will tell you all about it.
Thank you. So Meristem Wall is it's a project fabricated through a very different process. It's about sand printing. So essentially, it's a process where you're creating layers of sand and slowly, layer by layer, building it up using a binder. So this project, this is a finished process. It's not something that we investigated. It's established out in the market. But we wanted here to look into, if we have this formal freedom, how can we work with the design process to create structures which are integrated and where function is delivered through the form of the material. Again, here the inspiration comes a little bit from nature, and specifically from the termite mounds that I investigated during my PhD thesis. And what's amazing with the termites is, on the one hand, that they use the geometry of the mound to create a physiological system. The mound is essentially a lung that allows the termite colony that lives underground to breathe and to replace the oxygen that it consumes. So they use geometry to create this intricate function that we can replicate. But the other aspect of it is that just how they organize and how they actually are able to make this structure that functions and works in so many different environments. So even though they don't have any architects or designers or engineers that tell them what to do. They have a process that always arrives at a functional structure. Particularly, the aspect we looked into was how the termites use the geometry to control the flows of air. So this enabled us to create a wall that is actually not a barrier uniquely between the outside and the inside, but it creates a flow system that we can control, and we can allow air and heat and moisture to move between the wall itself, between the outside and the inside. And this is controlled actually through a little set of actuators that oscillate the air within it. But the complex geometry actually prevents wind, for example, from blowing straight through the wall. One of the things that came from this, that we can control the flows, we can control the moisture level, make sure that it doesn't get too wet and also doesn't dry out, is that it enables us to create a bioreceptive exterior. So this wall is actually intended to be populated and colonized by nature, and not by kind of a green wall with a full controlled species, but the wall is made so that it can be, grass can live there, birds can live there, insects can colonize it and become part of it. And one of the elements we used for that, as you saw in the previous slide, is the texture of the wall, but we also worked with these compartments and their variability, their size, the bigger and the smaller, to create a richness of ecosystem niches for different species, animals, plants, fungi to live in. The wall is made through a system of self-organization, so it's a generative model that incorporates actually all of these needs and functions that sits in it. So it ranges from the bioreceptive, from the structural needs, to this kind of system for shunting gas across the wall, but also incorporates things such as electric wiring and plumbing and windows. All of these are integrated into a parallel model, and they self-organize in an efficient and optimized form, which is then entirely expressed through the use of a single material. And as you can see, this kind of allows us to work with existing building practices, existing structures, even though some of the walls are very novel, some of the elements of it. It was 3D printed by a company called Voxeljet. As you can see here, their biggest printer. It actually is capable of producing elements that are 8 cubic meters large in a single go. So it's made from sand and a binder. But in our case, because we were moving this wall not to an existing building, but to an exhibition in Venice, we actually made it in a lot of small components that were then shipped here and assembled on site in Venice. And that kind of is a good highlight of the incredible precision and accuracy. So even though this process is actually able to make these big components of this size, full building scale, it's a very, very precise system. We also worked with the interior surface in a fascinating way, and together with Mariana, where we figured that the interior surface needed to be something than this sand-printed wall. So but we also didn't want to just put something on top. We didn't want to end with a normal plasterboard or something. So instead, we created a fully integrated CNC netted textile that's, in this case, not formwork or structural, but it actually forms, on the one hand, the surface, the ductility of the space on the inside, but perhaps even more importantly, it also forms part of the function in that it becomes a filter that allows certain things to pass through from the wall to the inside air without necessarily having particles, sand, dust, or insects, for that matter, coming into the building. So it dealt with tactility, acoustics, filtration. It actually had a very important functional role. And what is really interesting is that we could be able to integrate this straight into our self-organizing 3D model. And through the work and the pipelines that Mariana have developed, we could actually create this textile so that it is custom-made to the custom 3D printed wall. And it fits right on top of it to facilitate easy assembly and disassembly. And that's the end of it for us, but here is the wall that sits in the garden of Palazzo Mora. And we essentially think that 3D printing of architecture, even though today it comes across as concrete walls in many buildings, you've seen so much work being done, not least by FTBT, and some of our projects here that just hint at the possibilities of the future and how we can really start reshaping how we do things. But thank you very much for your time, and I will pass this pass to Mariana.
thank you, David and Anna, for the nice presentation and this nice contrast between a biomaterial and a 3D printed sand wall. It's very nice to see this at different scales, especially in contrast with the previous one. We will go to the last but not least presentation of the day from Fabian Luthrop. Fabian lives and works in Darmstadt. After graduating in architecture, he worked in various architecture offices in the field of existing buildings and began his academic career in plastic design department of the TU Darmstadt of Professor Ariel Auslander. Since 2012, there has been a continuous work in research projects in the field of traditional and new materials, in the field of architecture and design, specifically building with paper. As part of the BAMP team, he is responsible for the experimental research and for building experimental models. The documentation of this work is on exhibit in the research project at the Venice Biennale, and it's really beautiful to see.
Thank you very much for the introduction. Thank you very much, ECC. You did a great job in the exposition and helped us very well, so it's an honor to be here, to sit beyond you. So I may start with a short presentation about where we come from and where we are now. I think it's useful to show our roots. Where is it? The yellow one, yeah. So who we are the Department of Sculptural Design. That means that we come from another part, so we don't do computational design, or we don't do civil engineers. We work at the university in Darmstadt. We're a small department. Those are my colleagues, and my colleagues come from the design part or the architectural part. So we have an industrial designer as well in our team, and our professor is a sculptor. So he's an artist. So the focus is on doing design work and working with our hands mainly. So we're doing research, but we come from our origin from teaching students of architecture. They learn at our department how to build space, how to work with space. And one approach is that they work with their hands. So they work with clay and maybe gypsum and doing models and stuff like this. So we try in the master seminars to involve them a little bit more to do specific design work where they have the opportunity to work with their hands in one-to-one projects. This is a project made by students from a colleague of mine. So the last material we integrated in our maybe research or in our work was the theme of paper. This is one of the last pictures that we had in a seminar about building with paper. The research was just to do anything with paper in a way of working with volumes and geometry. And this was when I described the history of me, maybe as well in the situation in the university, this was 15 years ago. So as you can see, it's just like a furniture for a booth. And you can see we did it with Rhino, and we used the material, and this was the material cardboard that we used in this time as well. And we used it without the means of the purpose. So we just use it as a material, just like wood or something else, because it was cheap in there. So out of this history, I tried to do in my research, if you just name it like this, or the working with students, always a focus on different materials, but always on different designs or aspect or situations. One of the projects I show now, because it's one of the projects we did with paper. It's made of paper boxes. It's an artificial thing, or it's an artwork for the Biennale in Rotterdam, the Art Biennale in Rotterdam. This is made by students, and it was a small project over a weekend, what we did with Markus Heinzler, for example. And another project, what we started 2012, it was the Instant Home. where we try to do or to build in a competition with students emergency shelters made of cardboard or paper that are foldable and that we can easily send to maybe Haiti or something like this. So what we did, or where we end with this project, was we built a box, a simple box that we just built with our hands and the knowledge we had. So, and we had a problem, or saw a problem, about the scaling of simple models of architecture to something else what you can use. So we had a problem with the material, we had a problem with the knowledge or the methodology behind building with paper. So we needed to find something else, and we found a person who is called Professor Schabel, who comes from the paper, or from the making of paper and the research of paper, and we built up the BAMP team. So it's an acronym from the German, because we never knew that it will be an international thing afterwards. So BAMP means Bauen mit Papier in German, but it's now it's the title of everything we do in Darmstadt, based in Darmstadt. So take a look on this map. This was what we invented when we started the project 5 years ago. So we wanted to begin by having a look on the fiber. This is up on where Mr. Schabel is, with the pointer over there anywhere. And we wanted to do the research of chemical functionalization and semi-finished products. And then afterwards we want to build parts of a house or elements, and then afterwards maybe focus on a real architecture or a real building. On the left side you can see the Ariel Ausländer, our professor. We were a part in a in a big group where the disciplines are really different, and we as a designer, and on the other side the engineers itself, it was a project for itself. So where we started was we first made an atelier. We created an atelier where we can work, and we had the task, or they paid us a lot of money for being creative and doing try and error things to figure out where we can just implement some things made of paper in the building of or in the creation of a house. So the main facts were the basement, the walls, and maybe the roof. And we just had a look on every part of a house in more or less experimental research. How we did this, we are a small group of persons at our department, so we involved a lot of students that they just designed several things, and some of the things were so good that we just put them and figured out some connection always based on the idea of bringing things together without glue or without another material. Don't do components and stuff like this. We saw a chance to layer paper or cardboard to give them a new shape or form. We were forming or reshaping them, and in specific methods in a tryout, and we tried to element things in the first way. All these things that you can see are already done by Shigeru Bano, Octatube, or so on, and maybe at the other departments at the ETH or Delft. So it is just a general view on what is possible and what needs to be done in building with paper. We ended up a little bit at our apartment with the architectural designing, and as you can see here is the big demonstrator with what was built in a second way for the exhibition here. And we integrated some other researchers who care about testing of the material and simulations. Static optimization was a part of it, and to create a beam or a simple building part. We had the fiber optimization, so there was a guy who had a look on the fiber and the machine direction and everything what makes the strength of the material itself. We had material optimization. It's about profiles and how to receive a beam or to go to beams. And at the end, I will show you maybe some approaches or ideas how or where we see the potentials of the material. So, if you want to work in the future with paper in building construction or anything like this, we need to optimize the material itself. So there's a possibility to do this because it's a thin material, and I think it's a good use for a beam or layer things. It's the same thing we do with wood in our time. We make it thinner and glue it on each other to have a homogeneous building part. We need to find new products made maybe by the material or the basic material that are on the market. We need to find out specific methods to build with paper or this specific use. I just call it a reasonable effort to have something in architecture maybe that we don't talk about architecture for 100 years or so, that we just find the possibility to have a shelter or emergency shelter for a shorter time, like 1 or 2 years or so on. We ended up with an exhibition that the idea was just bring everything together and show it the audience or the visitors, and the exhibition is now here. A great thanks to the ECC because we weren't here at the time and we couldn't build up the exhibition, and we thought of doing the exhibition because we wanted to build it by hands, and it's about 1,000 parts that needs to be bring together and glue on the walls and stuff like this. So the exhibition works really simple. We show everything what we did in our project. So we started with the material itself and we ended up with maybe the first design of an architecture what could be done by building with paper. Maybe some smaller points. This is the material side over there, and we just placed everything on the wall. And the walls itself is made of paper, and this was an approach we had when we did the exhibition or the concept for the exhibition, that we want to give them give the room something like an image of a paper structure or a whole paper thing. So. Someone of them called it, we made a dialogue with the room, and we just copied the ornaments, and we thought about I lost the word for Gesims, but we copied the volute and the base and the claddings of the walls that are normally in the rooms. So this is the image, and it's an image based on the research, what we did and what others did. And maybe at the end, what we can do when we talk about building with paper, or what should be the next step or so on, what we did in this project is not really is research. We did a lot of thinking about what could be, and maybe what we can do as designers or architects instead of engineers or civil engineers who needs to work with the material and doing structures and things like this. We try to just change the image by exploring the paper. Thank you. That's it.
Thank you very much, Fabian. That was very interesting. I think it's absolutely beautiful to see a material that we don't usually associate with construction also being shown in so many details in the construction section. I want to thank everyone, because for me, at least, this has been a very stimulating session to see all of the different scales at which this relationship between design and material and technology comes together. So I wrote a lot of things down because actually there are very many things I would love for us to discuss. I don't know if we have a lot of time for that, but at the end of the discussion there will also be a chance for questions from the audience. I would like to very much try to structure the discussion going a little bit from the zoomed in material to a little bit of the zoomed out application and architectural context or construction context. Let's see if that also works in the follow-up of the questions in this way. The first part that I wanted to look into was a little bit of material and process. Somehow a commonality between what Marirena showed and what you have shown is this working with an imprecise material with a precise process. And how can you reconcile that? How can you make, of course, a lot of this is prediction, you're going to say, but there's, I'm sure the answer is different for both of you, but how do you reconcile working with an imprecise material in a very precise way? And should we be incredibly precise, and to what degree?
Yes, okay, I can pick that up. I think for us, the contrast between the two projects was very interesting in that perspective, because on one of them we had full control, and in the other one we don't necessarily have full control at all. It was a very touch-and-go process, and some of the inaccuracies were there, and they didn't. In some ways they didn't matter, and in some ways, of course, they do matter a lot, because they also relate to continuity aesthetically, but they relate to, in this case, to continuity structurally as well. But to me, the biggest answer just lies in a process-driven approach. So if you take the traditional kind of design methods of working through a form, so we create blueprints as engineers and architects of a form, and that form carries meaning, it carries function, and all these things. And that assumes that we have a process of manufacturing and construction that has very high precision to deliver that form. But if we instead work with a process-driven approach, we can actually start incorporating those inaccuracies of the production into that process itself. So it doesn't have to be predetermined. We can allow ourselves to see where things go, and we can adapt. And we can even incorporate into our very design and production models the adaptation. So that's where biology again becomes a very good teacher to us, because in biology you don't pre-plan, you work with what you have. And things that come out of the production, they actually influence how the future construction and the future production happens. So the feedback systems become incredibly important. So you have to have established in one way or another a feedback between what's actually being produced and the next step. And I think it was fascinating before when you mentioned the local versus the global, and kind of having a local design process. And this is, of course, about local in space, but it's also about being local in time. So we don't necessarily work with a global time frame. We don't have the end result known, but we work locally in time, and we respond to the changes that happen.
Yeah, to that, I would only like to add that, of course, it's been a kind of learning to put a bit the balance of where the tolerance needs to be. Of course, by developing the material and the scale of the resolution and the fabrication, all these were decisions that we made as we developed the process and understood the organism and the growth and its morphologies, particularly in the bioprint method. So we worked towards highest resolution up to a point beyond which it wasn't necessary, right? Of course, because each material has its own ways of relating to other materials and how it fits, right, and its own logic. And yes, beyond certain implementations that we achieved, whether we did to increase the tolerance, I think after a point it wasn't as necessary as in the other project, right, where we had very tight fittings and tight tolerances. And yeah, behaviors are the high resolution behavior of a material was within the print, and then the continuities at the global scale were working on different tolerances.
Yeah. If I can add a little bit on that, I think, as you said, it's very much about the process and how you design the process, but also as a profession, we are kind of spoiled, I would say. So construction is very industrialized. We are used to working with very small tolerances. So we expect, basically we design in digital tools that allows us to design in sub-millimeter scale with very almost zero tolerance, so very high precision. And we are used to expect these to be translated in on-site. So we are used to receiving materials that fit perfectly, that can be combined together. But if we want to incorporate other methods or other materials, we also need to adapt to that kind of thinking. So if you're, of course we develop, let's say, kind of very precise processes, but that doesn't mean that the final product needs to be as precise or that the materials we're working with need to be as precise. So if you need to account for imprecisions or materials that are by nature imprecise, then this has to be developed into the system that you're designing with. So, for example, with the bamboo, of course, we couldn't work with one single diameter or straight canes even or so, but this is a process or a fact that has to be taken into consideration. So you have a very precise material, and then you need to combine it with something that is super imprecise. So this is, in my opinion, I think part of the design and the process. So how to combine those, that to have an efficient system that works together and allows for this kind of, let's say, organic relation between the two things.
I also think we need to think about where the precision needs to be, because precision very often becomes something that has to be uniform, and of course that's not necessarily the case. There are moments when precision is incredibly important, and there are moments when it's not so much. And I think your Knit Canela project is a good example of that, where you kind of have the interfaces where you're fixing it to a frame, where you potentially are connecting to another building or another material component, where it really needs to be very precise. But the exact curvature of this thing in the middle might be less important, or maybe not.
To make a small comment to that, yes, indeed, that is, I do agree with that. But sometimes precision is important if we want to reduce the amount of material that we use, because then when we come to these small sections, that precision becomes actually a lot more crucial than when we have the mass to take this up. So in some sense, then the question would be, where is how can these types of sustainable materials or different types of systems, new materials, be scaled up so that we can use them in a construction context? So I would actually, because I like to jump in maybe and maybe ask Thomas, because you've worked on a big project actually. And to see, and even though that's not necessarily bio-based materials, if we talk about the question of scalability in terms of implementing this into practice, where do you see the biggest challenges in industry in being able to implement these types of new approaches, and the biggest hurdles that we have to surpass?
Thanks, Marianne, for the question. I was halfway expecting a more critical question, which is why did you use steel and aluminum for the building that I showed in Singapore? I mean, it's really a question of scale, right? If you remember from my presentation, the pavilion spans about 50 meters, has a height of about 16 meters. So as much as we would have liked to explore other materials, given the reality of the project, that it had to be constructed very quickly, very precisely, we didn't have much choice. Of course, this project was already designed in 2015. We have certainly experimented with other materials since then. Bamboo is a very popular material that a lot of our colleagues at SUTD experiment with, a lot of the students experiment with. And it actually makes a lot of sense in the context of Singapore. However, if we want to push with these experiments beyond this kind of scale of proto-architecture, right? I mean, it's often at the scale of a small pavilion, maybe. I think we've seen a lot of these throughout the world, but the real challenge is in scaling it up and making it a real building, right? And I mean, you see the background here. This is Singapore as a high density city. So yes, you can do small projects, but most projects are actually rather large. And I think that is the challenge. And I don't have a simple answer for you. I think there's some very interesting experiments with materials, for example, the reinforcement of concrete with bamboo instead of steel. This is something that was done by a colleague at the Future Cities Lab here in the Singapore context. I think things like this are quite exciting and promising, but we have to, I think, also accept the scale of architecture and cities in many parts of the world. And we have to find strategies that can actually allow for this kind of scale to happen.
Use different materials. We can produce these complex geometries. So, yay! But what can we design with them, or how can we take it to the next step? I think this is a little bit more of a blanket question that I would say that you're free to take up. But in the question of what do we design, if I can come back to you with the relationship to technology and craft, where do you see that placement between where we use technology, where you use craft, so that this becomes actually something also socially acceptable and also for a new material?
It's up to me, yeah.
Yes.
Yeah, okay. Thank you for the question. So I may start different because the material, what we use, is not new. It has a long tradition, and there's a process, an industrial process behind this. This is so complex and maybe one of the biggest machines that engineers build. So what we need to do is, in a designing process to think about what could be with an old material in a new process of maybe building houses. And our steps should be for the focus on building with paper, simple steps like how can we, with simple ideas, bring the material in building construction, like a helping tool for maybe protecting surfaces or so on while constructing, or helping to do a structure like your structure. So I think design process in this way can make somebody else who's doing the research up on the material. It's now at the time the industry. The industry is really static. It's just like they don't move. They see that everybody no one has a printer at home or so on, and no one used the paper, just like what we have here or so on. And there's a turning point, and I think we need to place these images of a new material, of a new use, or of a new process to bring them together, to bring research together, and to start a new structure working, or a new paper-based house or construction. I don't know if this...
Yes, I like your answer because it touches upon an old material that is maybe used in a new way, or needing to be accepted, maybe because it's not the conventional materials that we associate with prosperity, as you pointed out, with the glass, steel, and concrete, and even more so with mycelium. So what would you think it would take to make these types of materials acceptable in a design scenario where people would actually want to have this implemented, or have this be part of the design and architectural world? Because probably this is one of the challenges, the acceptance of a new material that is not the classical sign of advancement or prosperity in that sense.
Because, I mean, of course, I feel that question is quite relevant when it comes to my fungi-based materials, as generally that's something we've been trying for a long time to keep out of buildings. So suddenly proposing to make buildings out of that, I think it's there are quite a few people a bit uncomfortable with that idea, right? I think, but the fact that it is quite a controlled and to a high extent, predictable process, I think can. Some of the questions that I think arise is perhaps, right, fungi and how do we prevent rot and molding and these things happening when it comes to specifically fungi materials. But I think there's, working with the material, we found some really interesting things, such as the fact that it is water repellent, right? So more so than without the fungus. And there's, as well as the potential that antibiotics, they do, right? The original is from fungi. So perhaps the material has inbuilt repellent towards other microorganisms. So these are some really interesting potential trajectories that, of course, we need to further test and to be able to guarantee such things like that. But I think perhaps at the root of that question comes also a shift in how we see architectural materials, right? And what should we expect from them, right? And whether it is the kinds of things that we see in concrete and we see in steel and glass. And of course, when you work with bio-based materials, it's not going to have the same kind of relationship to and the same performance, right? Structurally, not the same, but in terms of smell and tactility and a lot of other things, I think change as well. So, yes.
I think a really an important aspect of what you're asking, these older materials we see them coming back a lot, the unpredictable, the natural materials, and particularly when it comes to computational design. And I think this has to do a lot with complexity. So if you go back to kind of before industrialization, the way we were building, the way we had a system that understands and deals with complexity was basically based on experience and slow change. And you had this kind of emergent process, which was craft-centered. And the advantage of that kind of process is that it allows us over time to build an understanding of very interconnected, complex systems. And then something happened, and we started having a more engineering-focused approach, which allowed us to kind of innovate very, very quickly. But the downside of that, I would say, in the, maybe the modernist paradigm, is that we simplified things. So particularly things that are responsive or dynamic or interconnected, we just didn't have the engineering capacity to deal with that because it becomes incredibly complex. And what we're seeing now with simulation coming back is that we can actually start coding these relationships into our design tools. So suddenly a whole new world is opening up to us where old materials that we've kind of phased away because they weren't efficient or controllable enough, they're coming back. And that allows us to be a lot more sustainable, but it actually also means these things can perform in ways that we only thought that steel and glass and concrete could do. And I think culture will follow that technological change in the way that kind of ornament became out of fashion just at the right time when engineering industrialization made it convenient. I hope a similar shift is happening with materiality. And I think this also is a little bit relates to the precision. Where do we need the performance? Where do we need the precision? The most big impact, perhaps, of concrete is that we have this amazing material of concrete with reinforced steel. It can do anything. So we didn't need to worry about all these kinds of geometries. We can do flat roofs, flat slabs, straight everything, because concrete can do anything. The problem, of course, of that, we started to realize that it's also resource intense, and we need to change the way we think. We need to start understanding that this performance is very important, but we need to apply it very selectively. We can't just, sprinkle concrete and glass and steel over our environment. We need to use it where we get a big advantage of it, but we need to replace it with other materials where they are equally good. And I very much understand, Thomas, what you were saying before, and I agree with that. But I also think that we have to look at the flip coin of that, the high-rise cities, the intense cities. Yes, if we want to build that, we might have to use steel and concrete and glass. But we also know that that's not a sustainable way forward, and perhaps we do need to think harder about how we make cities. If we need to follow a material paradigm that's more natural, that's less high performance, how can we still build a city that works without having high rises, for example? And I think that's a huge challenge that we have in architecture moving forward, and that it doesn't only involve kind of us who are technical specialists, I guess, in a way, but also the larger architectural community in terms of, okay, we need new typologies, we need new ways of relating to our environment that respond to these material developments.
Thank you.
Can I just jump in here? I just want to say I fully agree with the comment that you just made. And of course, there are very interesting developments that we see throughout the world. For example, timber is a very interesting material that also high-rises can be built out of. There's some very interesting upcoming projects, for example, in the context of Japan. But since you talked about, the architecture and urban design being, complex, and, if you apply a certain kind of systems thinking to the question of sustainability, of course, then you also have to see that the dense city is probably a more sustainable model than, the not dense city, right? So many European authorities actually come to Singapore and other places to understand better how you can actually combine density and livability of a city, because they also understand that building, laterally is not the way forward.
What we somehow agree is that there is a need for a sort of cultural shift, so that there's an acceptance of new materials, but maybe also that is there a need probably to understand how these materials can be scaled and where they can be scaled, because as you pointed out, maybe we can do a lot of things with biomaterials, with wood, but they're not going to be applicable in all contexts. So kind of the question that I have coming out of that is, how do we act on a local scale with these materials, having a sort of sustainability in mind? Because if we try to make everything out of one material or in one single way, this might not be always the most sustainable answer in terms of our resources or resource depletion, whether they are fossil fuels, natural resources, or not so much.
Yeah, but if I may add on that, I think you're totally right that we're talking about local solutions, and when we're talking about scaling up processes and what materials we use. So it's not possible to say, okay, this is the most prominent way, let's do everything like this. It's also not viable to say we only build vertical or we only build horizontal. Of course, we will have dense cities, but we will also have a variety of buildings, a variety of typologies, and a variety of functions. And for all those, we need to figure out what works best. So different systems or different combinations of systems. So even if you have a steel frame, this doesn't mean that then all the materials inside need to be steel and concrete and so on. But there can be combinations, and I'm pretty confident that we can find solutions for the future. And I understand that there needs to be a cultural shift, that we have kind of this acceptance of new materials, but on the other hand, I think it's also maybe a little bit late to let it become very organically or to accept this in a very organic way. So I think it's very much up to us, and this is why research in this domain is very important, I think, and the demonstrators, even if they're small, I think they're important because they help us convince people that these new systems or these new paradigms are performative and they can be a solution. And by these, we can convince people that we need to change how we think. Because so far, let's say beyond the architectural realm, all like very known offices and prominent architects, and magazines and so on. So it's a whole web that promotes this image of shiny objects, of even of computational design and new technologies. It comes with this kind of shiny covers of, I don't know, shaped metals and very finished touches and so on. But this is not all we can do with it, and maybe this is not what we should be doing with it. So by exploring, showing the world what can be done, and educating people that don't know many things like that are inside our profession, we can somehow push forward this shift towards the future. Yeah.
Yes.
And for me, this is the point as well, because I see all these pop-up architecture and pin-up architecture and so on, and this is really cool because it's the edge. No, it's what is now really famous at the time. But I think we have to step back a little bit, whether we are in Germany or anywhere in the world. So for me, it would be, I would say the focus should be on simple systems of building system, just like an inner wall or so on, because there's a great possibility to bring in, for example, just in an inner light wall to use something else than gypsum board or so on. This could be an impact for the building industry, for wide building industry, instead of doing pavilions or so on. This is the other part. So if you just want to implement building with paper or so on, for me, it would be the way to have simple systems made of simple architecture that you can place anywhere in the world. And this would be, you talked about the fear of people who have a fungi in their house or so on, yeah. So this is the theme. If we talk about architecture made of paper or cardboard or so on, everybody says it's a burnable house, or the house to burn, or the humidity or so on. You have to control it. So the first step need to be, we need building parts and objects that we can use in the regular architecture in the simple houses that everybody's doing. So we could do something with our design, and these are the demonstrators we can build now at the time, because the material is not there. So,
if I can just follow on your question as well, I think for us specifically in the biomaterial project, I think it's an interesting combination of, because I definitely agree that in terms of resources, I think locality and local resources are very important, and in that sense, for our material, plant are everywhere, right? So residues from industries, they're all around the world that can be used for this, and as well as fungi, they're everywhere, right? There's we don't even know exactly, but an estimate of millions available, and we're just tapping the surface of it. So their performances and the ways that they can be used, I think, is of a very high degree. So for us, this project resulted in a very local wood and local fungus from Sweden. But I think this can be implemented in very different ways, and with lots of potentials of performances around the world, right? With their local fungi and local fibers. But at the same time, globally, just the technologies and the computational models, and I think this is where we can, as was says yesterday, like think globally and act locally, right? I think the global perspective can be in the use of technology and the sharing of the knowledge, but then applied in very, very local context with local resources.
I think it was perhaps in the first film we saw where it was mentioned or pointed out that it's in the global south that most of the construction is going to happen. That's where the current population growth is happening, and it's also where the fastest increase of wealth is coming about, which is incredibly encouraging, but it also means we need a solution for different places. And I think the danger is if we apply kind of a European building paradigm to these places, partly because they don't have infrastructure built out, infrastructure of roads and of factories, of centralized systems, of ways that things are done. So there's an opportunity to do something new, but they also have very different climatic conditions. I'm from Sweden. We're very used to passive house, and it's very difficult not to do that in Sweden because it makes a lot of sense. But if you go to Northern Africa, where we take a lot of our students to think, suddenly the logic of the building physics is radically different, and you have to work in very different situations and find different solutions. And not having the local infrastructure is actually an opportunity. And the same way that mobile telephone actually was easier to catch on in many third world parties than in the West, because they hadn't dug down cables everywhere. There's an opportunity to do things newly in a new way. Whatever local material there is, we can share information, we can share knowledge on how to treat that, we can compute things. And we don't have to rely on standardization and standardized components and materials, but we can build relational models and design tools that allows us to work with whatever we have available at the place.
So leapfrogging.
Yes.
Sorry. That's a very nice point, because it is true that all of this happens in the global south in a different context, and we're sitting here talking about it somehow. But this is also where that acceptance, or that cultural acceptance of a different material or an old material, also would come in, because how do we shift maybe the certain values that we have associated with certain materials in certain contexts and convince somebody that they should live in a mud house, or that this is the most sustainable or the best way? Is this the best way to act in those local contexts? And how does one change that image of paper, of bamboo, of mycelium, of other materials, in a way that they become also an image of something that is acceptable? And I know this question probably doesn't have an immediate answer. So, so somehow, what I wanted to follow up with that is also with an example from what you said before. You said, okay, maybe we apply this in a particular context, and there's a question of future-proofing a design or a material that you use. Usually when you try to future-proof this, it becomes a lot less sustainable, right? We combine it with other things that make it not burn, not decay, not rot, not do any of these things. So how do we think of the different timelines or the different lifespans of a design given a new material, and how much material then we will be using locally, so that we don't end up in a sort of overconsumption like we do now with concrete, for example? Because having the material everywhere and we can keep using that doesn't mean that we won't end up in the same paradigm of non-sustainability even with an ecological material. So do you think there is a possibility that we have timeless designs, or designs that can last for a longer time, instead of us just always making a new special design that is a little bit of a...
Yeah, I can try to answer this. So I think, first of all, anything's possible. It's more that our minds put barriers just to make things easier a little bit, but first of all, I think because we tend to think with the things that exist today, but this doesn't mean that the way we create, for example, composites today, or that we sealed materials will be how we do it in the future. Maybe there are also researches that look into these topics, so how to seal the materials from decay. But I think there's also a different aspect that we can look at, because we have a paradigm that we design a building that should last for, 50, 100 years or so. And this is also due to the fact that we have been designing monomaterial systems, concrete buildings that cannot be, you cannot replace parts and so on. So it's very difficult to, once the system is damaged, that you really fix it or so. Or it's very labor intensive, let's say, to maintain it and fix it and so on. But if we design a little bit in a different way, if we design in a more modular way, for example, maybe it's also okay to have smaller time spans for different materials. So there are buildings, for example, in the south that are made of mud and so on, and the whole community gathers up every year to refinish the building and so on, also in terms of public infrastructure, religious buildings and so on, and they do it to maintain their buildings. That's maybe on the other side, so every year having to refinish a building so it doesn't decay, so the rain doesn't make it go away. But I think designing for a fact that you can have exchangeable systems and exchangeable materials in a healthy life cycle. So by using biomaterials, you can say, okay, this is the lifespan of my material, this is harvesting cycles, these are production cycles, and then you can design for that. So I think this is maybe a healthier way of looking at things, of knowing how fast you can harvest and produce new materials, and making sure that you replace the materials that you haven't had and reuse them in a certain way, or find a way to compost them, or whatever else you can do with them.
If I can follow up on that, I think that's quite interesting, the relationship between the timeline of a material, and it's the resource availability and impact it has, right? So I think, because you mentioned a few times, I think the really interesting both material systems and computational systems for extremely high precision, right? Minimizing as much as possible the material use, right? And I think that's actually really important and really relevant, especially for very large scale, high density, high performance skyscrapers and things like that, right? For that use materials that are, high energy embodied and potentially scarce, right? Like concrete and steel and things like that. And I think for these it's important, they have a high energy input, right? And then it's important to use them wisely. And therefore their potential is also that in a very large time span, right? That high energy embody is reduced, right? The more we use them. But then when it comes to biomaterials, I think they behave quite differently, right? In the sense that they do last a lot less, of course, but then also the energy that it used for them is a lot less, right? So they need to be replaced more often, but then they cost less, right? And in that sense, if we're able to grow them locally and to use them more, right, even if they need to be replaced more, I think, I think it just makes us change a bit how we think of the life cycle and the care and the repairing with the different material systems.
It's very easy, I think, when we're working with innovation to think that everything is sustainable because it's so small scale. So, of course, it's going to feel a lot more sustainable to work with these novel materials that's kind of made in a little tiny workshop and place compared to the giant construction industry of concrete and steel. But if we were to replace all the concrete and steel with biomaterials, how do we source them? And of course, if this means that land use-wise, we're going to have to growing, energy forests on millions of acres of what is today wheat fields, for example, that's also not a sustainable solution. So scaling up is always going to be our massive challenge. And I think that's one of the key components to kind of the mycelial project we have, and just its ability of working with different strains of fungi, different processes to actually recombine and remake these materials. Perhaps a building that's built from similar materials needs to be updated and constantly improved, changed, replaced. If that happens in a giant farm in a faraway country and this material is constantly shipped, that's not sustainable. But perhaps if the roof of the building also incorporates a kind of a small energy forest or something that actually is being grown there, and that material can be constantly made and recycled and turned into the building itself. Of course, these are kind of far away scenarios in some ways, but I think it's really important to start thinking about how we're scaling up these processes and how are we sourcing the material we're going to use, because it's not automatically sustainable. Architecture, construction is a huge problem in terms of sustainability, but so is agriculture. Human agriculture. The biomass on Earth in terms of mammals, for example, I think it's over 95%. That's combined humans and human livestock compared to the wild animals. How do we leave space on the planet for for a biodiversity, for ecosystems that are not used and consumed by us. So I think these are, you know, enormous problems that have to be tackled in relation to this.
Probably.
No, monoculture is not a good thing.
So probably we have.
Mariana, can I
Yes,
just
absolutely.
add something? I mean, I know I'm hovering in the back, so you might not be able to see me. I think this is a very interesting discussion. I think the thought I want to add here is, you know, in a way, I feel the most sustainable building is actually the building that's already built, right? Because tearing buildings down to build new buildings is not actually a very sustainable approach. And I think particularly in the context of Singapore, it's quite shocking to know that the average lifespan of a building is just about 16 years, right? Because the real estate pressure is so high that constantly things are redeveloped. And of course, you can imagine that this is not a very sustainable way forward. But the thought I want to add here is, I think, you know, we have to look at the whole issue of adaptation of the existing building stock. So not just think about new buildings that we build from wonderful materials that have certain properties, but also, is there actually an opportunity to use some of these new approaches, be they computational, be they through new materials that have certain properties, to make a significant change to the buildings that are already out there? Because as I said, I believe, you know, the most sustainable building is really the building that's already built.
Very good point. And especially in the context of Venice, of being here, or in Italy where everything is already built. Since you're not hovering in the back anymore and you're full screen now, I can see you. You were mentioning the question of productivity, and somehow and fast production, and all of us in our presentations to some extent went, and now this is a lot faster because we have computation, because we produced it fast. We did everything in 3.5 months. We did everything in less than 6 months. We did everything in 2 weeks, and so on, which is great. So we're all promising that we can have this very productive means of doing things. So I'd like to look at the challenges of that, because in some way, in all of those projects, what we do is we take up all of the roles in a value chain. We become the designers, the engineers, the fabricator, the assemblers, the entire process. And that's not usually how this happens in construction, right? They're all different actors and they work at different scales with different knowledge pools. So what are the challenges that we need to overcome in order to be able to implement these kind of very fast integrated design and fabrication processes in the real world? And maybe in that sense, I would be the first to ask you, because you've done this at a particular scale, and I suppose you've done this together with industry then, or with partners.
Well, I think what's interesting about the project that we did in Singapore is, I mean, the fact that we took on roles that, you know, typically in a more traditional environment would probably be assigned to other disciplines, mainly structural engineers. So in our case, we were actually able to do a lot of the structural optimization, the fabrication aspects, the preparing of the cut files for the aluminum sheets, and all this was actually done by a team of architects. And I think some of the speakers that we have here today, I mean, they all pointed out that they're operating on this kind of threshold of architecture and engineering. And I think generally we have seen this shift, right? That as architects exploring these new tools that we have at our disposal, they allow us to do things that we were previously not able to do, right? And all of a sudden enter into the realm of engineering, even though in our case, it was always a classically trained engineer who had to sign off on these things, but all the geometry and all the phasing of the project, all of this was essentially driven by a group of architects at SCTD. So I think there's an interesting kind of merging and shifting of fields that is really driven by these kind of new computationally driven methods and tools that are out there that are quite interesting. About the acceleration of some of these processes, I think this is a bit a double-edged sword, right? I also believe that good design takes takes time. So we have to be allowed the time to step back and look at what we have designed, and is it actually the best thing to move forward that way. So I'm quite scared when some offices actually in China, in particularly, they pride themselves in being able to put together a project in just a week's time, a large scale project. So again, I think this constant acceleration of processes is good on one side, but it's also a bit problematic on the other side. But I would love to hear what the colleagues have to say about this.
I'd almost like to go back to the nature of craft here, because I think, that's almost what's common between what we talk about. These are very much craft-centered approaches. It requires that we as architects or whatever we be, we have to understand the process. We have to understand the fabrication, we have to understand how it comes about, and we have to understand where it's placed in order to make the design. We're kind of leaving this thing that where we as architects are creating something, handing it off to an engineer to figure out how it's built, and then a constructor to build it somewhere. So I think this is really shifting to what we need to be as architects, and it requires us to have a completely new understanding, and that understanding, I think, perhaps was never possible before these computational tools came about. So to me, it's incredibly important that architects gain this ability to become part of the project, to use these tools as craftspersons, because it's a very, very different thing from the kind of automation of design that you see in many aspects of digitalization, and that you're mentioning with these kind of giant offices that can deliver enormous projects in such a short time. Through all these things that we're trying to get away from in the construction and manufacturing industry with standardization, repetition, this kind of mass production of things. And we're going to mass customization. And we as designers, as architects, as engineers, we need to be part of that process. We need to change into mass customization away from mass production. And this relates to me very, very much to the question you introduced before about how do we gain acceptance for these new materials and new processes. And the key is of course, community. And we have to work with the communities. And there's a marvelous project we were seeing before in South Africa. It's a really good example of how these things can come together and should come together. But again, it's only when we as designers also become craftspersons. And we engage with, not only understanding the logics of the computation and the logic of the material and the fabrication process, but we understand the logic of the community. And we apply that knowledge to kind of guide the community's needs. So, mass customization is not just a manufacturing paradigm. I think it's also a design paradigm that we as architects need to adapt to.
If I can disagree a bit. To a certain extent, because you said that before we're not so much in contact with the craft and so on. I think this might have been true when we shifted towards mass production and industrialization, but this has not always been true. Before that, I think architects were very close to the craftsmen, and they knew what was possible within everybody's craft and so on, and they designed for that and keeping in mind that. And I think this is also kind of this case where history repeats itself, so I think we have been moved from that model to kind of mass production where the profession became a little bit of using the parts that are out there and synthesizing a bit those things in order to produce things. And now there's again a shift where we rediscover a little bit this relationship that existed before. So I think the role of the architect has always been, maybe in a sense, kind of to bring everything together. So we are kind of the orchestrators that we need to understand the different disciplines, the different needs for everything we design, and we kind of are responsible to bring everything together and point to where we want to go. So probably this is another leg of the cycle that we are entering. So we are now rediscovering the crafts. I think we are trying to get in touch with people that are craftsmen and how to digitalize the craft, or how to bring a new meaning to their craft with new tools. And this is very fast now because it's at a prototypical scale, so we're mostly constructing in smaller scale, but I think when this is picked up by the industry, moving towards mass customization, as you say, this will slow down a bit, because when we try to scale up and when we try to fit everything into production lines and so on, things will not be able to be produced in weeks or in a month and so on. Things will again take time, so we can produce things, we can fit into patterns and so on. And this will slow down until this process in the industry is again optimized somehow, that it speeds up again. And probably after that there will be another cycle, I don't know what, but I don't think it's kind of like this new era that has never been visited before. So looking at it from a more macro scale, I think there is some kind of pattern.
Yeah, I fully agree with you there. I think, yeah, we don't have to go back much in time, maybe only 50, 60 years to go to an era where we were much more craft-based. Yeah. I think the word vernacular is an amazing word in that it somehow represents architecture that's come to become very undesirable. But the word itself actually just means, architecture or language or whatever that comes from its context, its local context. And, international style became this thing where everything was supposed to be the same, and we kind of put that on the pedestal, this global movement, and we're luckily seeing a reaction towards that now, and we are starting to see that things that emerge from their particular context are incredibly positive. So I think it's also perhaps time for a revival of the word vernacular, as not just looking at what was in the past, but reusing it, bringing it back, engaging with it.
Yeah, and may I? This means also that we have to go back to the discipline of architects and architecture itself. So in the last time, a lot of architects just went to other professions or other themes or so on. And that what we try in our teaching at the university, because of maybe the budget as well, so we make it simple and we try to teach the students, so the young architects who professionalize themselves in the future or for the future, we try to show them how to craft, so how to do things with their hands. So I think it's a discussion of the discipline and competence of what we should do as architects. Are we researchers? Are we civil engineers? Or are we architects and bringing things together? So this is, for me, the main question: what is the discipline of architecture in the future? And or for architects, not architecture.
And what is education for maybe different disciplines that have to work together, and not only architects, because probably we bring all of these kind of disciplines together from the early stages. So that's a little bit of the synopsis of what you all have been saying. I think we have to go to the questions from the audience in the interest of time. So are there any questions from the audience?
Yes, we have from the YouTube channel. I don't know if anyone else want to say something before.
Okay.
Thank you. I have a question about the shape of the architecture you've all been showing. Because we talked a lot about construction and we talked about technology. But all of these projects and objects, they have a very specific shape. And I'm asking that because of in front of the background of the cultural aspect of this shift that we all agree is necessary. We've seen in the Singapore example that there was a certain appropriation of this structure, that maybe also in a context that is very young and very fast. It's easier to also appropriate these new shapes and new forms. But how do you? I mean, it's a question for all of you. How do you see this? Shapes being accepted and appropriated by a wider range of people beyond the field of architecture?
Can I take this since the project in Singapore was mentioned? I mean, the shape of the pavilion was, as you also said, was actually driven by programmatic needs, but it was also driven by the combination of these temporary exhibition domes that I showed in some parts of the presentation, but at the same time, of course, the orientation of the building, the perforation of the skin, all of this was driven by structural optimization as well as a kind of environmental optimization. So in Singapore, as a tropical context, right now it's just before 7 p.m. and we still have 30 degrees Celsius and very kind of high humidity. So it's all about, you know, shade and kind of using the wind that you have at your disposal. So the orientation of the building and perforation of the skin were very much driven by a kind of a wish to optimize catching the prevailing winds as much as possible, and in a way fine tune the perforation such that we can even react to a tree that is right next to the pavilion and the shade that can be used for opening up this structure more and then allowing the wind to go in. So in a way, as I'm sure you're aware, architecture is a wicked problem. So you always try to bring together many things. Of course, there's also the aesthetic component as well. So we were interested in this case in the shell structure, not just because it's structurally a very efficient form, but also for the expression that it gave in the particular context that it sits in. And actually in the background here, this is Gardens by the Bay. So you see there's already a certain formal language in place. Regarding the acceptance of the project, there are not many projects like this in Singapore. Actually, I think this was the first one that looked like this. And it's quite telling that it was pursued in the context of the 50th year anniversary of Singapore. I wanted to be kind of forward-looking and future-oriented and so on. The acceptance, frankly, completely overwhelmed us because the project was so popular and it appeared on web pages, you know, like of local banks and this and that. And all of this eventually led to the government to decide to keep this project, which originally was meant to be a temporary structure. So I think acceptance-wise, yes, it is something different from many other things that we're used to. But at least in the context of Singapore, the acceptance was there almost from the very beginning, with the Prime Minister tweeting on the day of the opening about how marvelous the structure is. So I think people are excited about these new formal possibilities that we have. And I think many of the projects that we saw today, I think they're incredibly beautiful, probably not just for the eye of a trained architect, but also for the general public.
Quick complementary thing, and I hope the answer to your question is diversity. And I think we as architects have a tendency to go very much for purity, especially in the beginning of things. And I think if you look back at the past 20 years of digital architecture, computational architecture, it's been very uniform. I think that's actually changing. I think there's new aesthetics coming into it. And because of the control of the process, we're not so much driven by software, we're driven by the manufacturing, by the making. And I think that's opening up a much broader language that hopefully can doesn't have to fit everyone, but it can fit many people through many approaches.
Yeah, also because it's possibility for, again, adaptation and customization. I think it can mean many things, but in a sense, it's also the form, at least in the way we are approaching it. Of course, it ends up quite perhaps particular and different, but it's also derived from the process and for requirements of the materials and a lot of performative constraints. So in that sense, it follows in a way the tradition of architecture materials and expression coming from the construction and tectonics. So yes.
But it wasn't, so in our project you can see it's not a question of shaping things or so on. We come from the background, from the sculptural design, so we should knew what is shaping or was the shape of an object or of a building and so on. But what was the limit in our work is we didn't work with the computer, so we didn't use 3D modeling or just like a grasshopper or so on. So we just work with our hands and with the material itself. So the material is this, what we have. So it's just a tube or a board or so on. And we just used simple ways to build a simple architecture. And that's why we decided to don't do these shaping forms or so on. We built frames, like artificial buildings or so on, in a way to just work on the image of the material, first of all. That's why there is no shape. And I think it's impossible to do the things in Singapore with a paper in the next 50 years or so on, but it could be a part of it. But this wasn't the focus. It wasn't the focus on the shape. Simpler things.
I mean, talking about form and shape, I think I also hope it's about diversity of shapes and forms, because somehow things in architecture are categorized as free form and rectangular or orthogonal. And this notion of rectangular or orthogonal, which came with much of the modularity and industrialization, somehow follows us today, but I don't think that it's still a question, how do we change this perspective? Because there has been in architectural discourse now since we were discussing blob architecture like more than 30 years ago and so on, or even before that when we had like in the 60s visions of space architecture and so on, we have been talking about freeform shapes and the potential of freeform shapes and more organic ways of living and so on. So I don't think that it's a kind of a black and white situation. We did not need to convince people, or at least this is in my mind, and I hope so, that we do not need still to convince people in 2021 that we need to shift away now from the rectangular shape to a freeform shape. I think this has somehow always followed from vernacular architecture somehow into computational architecture and the possibilities of computational architecture, and I actually think that this is a very interesting time when we kind of see the two things merging together. So computational architecture with vernacular architecture and how these free form shapes start to make sense now, and it's not just blobs.
If I can also complete, for me it's not so much about the shape. It's definitely not about being freeform, and it's not about the aesthetics of the particular objects that we show, or that it's about kind of demonstrating these things in an extreme context of something that we can do. For me, the geometry is in terms of efficiency, so if we can be efficient about things, and then take those principles that are demonstrated in an extreme way and be able to apply those to our everyday needs. If we can design, and that is a good question, if we can design whatever shape in this way and we can build it, what should we design? And I don't necessarily think that it is the shells that we're showing that we should be designing, but if those principles come back to give a certain quality of space, a certain quality of life, a certain quality of function, and a certain quality of sustainability, if they come back to answer the questions of architecture and environment in different forms, then they do their job. So then they will also be accepted, but maybe not in this particular aesthetic, but in a way that informs a new way of doing things.
Yes? Oh, wow. Yeah, I have actually, thanks a lot for this discussion, because I see a lot of links also to the discussion yesterday where we talked about changing the culture, acceptance. I really like this notion of creating acceptance within the communities, within the users actually. And I'm wondering, maybe part of the transition would be to create acceptance also from the industry, and not just for, the methods actually, but also when we look at certification, like what do we actually build for? Traditionally, we always build for safety, safety of like creating shelter, creating protection from, weather, all these things. So I think part of our culture so far has been to create safety for, I don't know, the lifespan of the building of 30, 50 years or so. We create one building and we hope it perform that, safety performance for the rest of its life without touching it anymore. But maybe we need to change that way of thinking as well and create acceptance that, we need to actually be involved much more in the timeline and the life cycle of the building. We need to come up with solutions on what are replacement cycles, and maybe also link that to the way that we certify certain materials from the start, that maybe they come with a exchange program or things like this, so that also the industries and the users and the people that actually have to trust that these buildings will do their perform their purpose, that they trust in those new materials that they will do the job but in a different way. So maybe, Mariana, you were asking before what's next, no? What is the next step in building through technology? And I would like to maybe pose an open question, how do you see our role in this maybe life cycle process, in maybe sort of maintaining buildings but doing maybe a step more in this? Is it the clear question, or yes? Okay, good.
Yeah, perhaps start then. I think we've been trying this as architects for a long time, and we've always perhaps been hampered by designing something that can be modular and can be replaced or extended in the future, and I think we really like the idea. But when we have standardized and proprietary components and systems, the problem becomes that they evolve. So what makes sense when we build something doesn't make sense 20 years later when we want to replace it. And because we work with standardized components and physical systems, it's almost impossible to replace them. But if we are shifting the standardization away from the physical into something which is virtual, so we're actually standardizing relationships that can be codified in the computer, I think we're going to be gaining a lot more flexibility when it comes to adapting and modifying and replacing buildings as they come forward. So I think it's just thinking about 3D printing as an extreme example, perhaps. It doesn't really matter if you're replacing a part of a 3D printed wall with exactly the same system, if technology has evolved, because you can 3D scan it, or you have the original file or whatever, and you can take whatever section of that building and you can replace it with something that fits perfectly into that context. You can codify its relationship and then having a new system coming in. So I think we technologically have a lot of opportunities moving forward to do much more of this than what we have in the past.
Maybe also creating these feedback loops that you were talking about, no? To really make that part of our design already, to plan those feedback loops and develop systems to actually make it possible to update only when it's needed, for example.
I would add that we really need to take the policymakers into this process, because very often these things are also slow, because even though the technology is there, the possibility because of regulation might not be there, or this understanding of it. So taking in the policymakers and the industry players into it from the whole time, from the early get-go, so that there is a little bit more agility in the way we can change, certify, and how our ideas of certification and what is correct change over time, to do this in a faster, in a better, and at the same time safe way is probably very important.
Yes, I think
there is one more question over there, if that's okay, from the audience.
Sure.
Hello. My question is more of like a comment first. I'd like to go back with what Professor Thomas said about basically that the most sustainable building is the one that's already built and reusing that building. So my question is for David and Anna, do you think that maybe the biomaterials can be used to restore these buildings that are, for example, I'm assuming in Singapore, more present, like high-rise buildings that are about to be torn down, and maybe with using these biomaterials, then will reshape the whole image of the city, and then afterwards, for very further future, we can also build the cities in this way. But first, maybe the first step should be actually to use this material to improve the pre-existing buildings. Thank you.
I think potentially yes. I mean, of course, it depends on a lot of things. It's not, but I think the potential of these biomaterials is that they can fit into existing structures, especially because their main role is not load-bearing, right? So they won't be able to replace concrete, right? But they can easily fit in a structural system that already exists, so as partition walls or external walls, things like that. Of course, we need to do further testing to really establish, and this ties to your question, Christina, as well, of course, I think we need to be more involved as material designers in assessing the life cycle, and I think designing with the plan for how are they integrated, how are they replaced, and how do they fit with the rest of the building elements together. But I think for sure that is a potential, yeah.
Maybe we can take one or two questions from the YouTube channel.
Yes, actually we are almost out of time, so I'll make just one more question. After all this presentation, we understand that there is a significant attention on materials and construction waste, of course. Do you think that, globally speaking, we are really going towards better architecture for the planet and for the environment, or it is still related to a niche sector of architecture?
That is a very good question. Well, the hope is that we're not doing niche architecture, and I guess the whole discussion today was trying to go into how are we going to get out of it being niche. For the time being, it is niche. The question is really how do we go beyond it? And this is very tough. It's a very tough question because it needs to latch on to design, to architecture, to construction, to materials, to acceptance, to society, to a cultural shift, to all of these kind of aspects. So somehow it needs a holistic I don't get the word now, ingreep. A holistic sort of intervention to be able to get there.
But I think I definitely see a shift in the conversation that's been happening recently, where we've a little bit stopped talking about how we're going to do things in the future, and we've started talking about how we're doing things now differently. There's a sense of urgency to the climate question. There's a sense of urgency to a lot of other problems we're facing as society, social ones as well as kind of ecological ones. And I do think that there is a potential of these things happening quickly. And technologically, it's been massively quick the last, and accelerating every year, I think. These things are going away from being niche explorations in universities towards being actually implemented in buildings.
I think where the biggest shift is in a positive way is to say that maybe 6 years ago or 5-6 years ago when I was working in an office, if you came up with this panel and these kind of solutions, maybe a contractor would have said, "You're crazy. You guys live on a different planet." And now, indeed, that discussion is not the same. There's an openness to hearing these solutions. There's an openness to wanting to work together. But I guess one of the crucial points there is for academia not to stay in its lane and industry not to stay in its lane and to actually start trying to work together towards this.
Thank you for your presentation, for your inspiring researches, and also for your positive feedback. Thank you.
Indeed, this was a very interesting and very stimulating session. I'm sure we can go further on, but we have to wrap up this session. So I personally think it was very inspiring to learn about all these tools, techniques, and mechanisms that we as audience probably we don't know, and we don't have the chance to know the background of how these things work. So it's fascinating how we've reached today and the conversation today, not just for the future, from putting knit candela and fabric inside the bag to the mycelium and paper-based construction and the use of local and renewable materials. Thank you, Timur. So today, I invite you all to go and check the mycelium structural wall found in Palazzo Mora. The very well-curated exhibition of paper by TU Darmstadt in also Palazzo Mora. And I also invite you to see the digital fabrication, digital building technologies lab, bamboo pavilion in Giardini della Marina Ressa. Have the chance while you're here in Venice and explore everything that we spoke about in this panel in the exhibitions. This is it. Now we're going to have a lunch break, 1 hour, and you can have coffee here from 2 till 2:30. And 2:30, we're going to resume with the last session for this conference. Thank you so much.
Warm greetings to you all from Cape Town, South Africa.